Welcome to Data Skeptic Time Series.
This is Data Skeptic Time Series, the podcast about how to predict the future based on historical sequential data. Episode number... I say table, you think chair. I say time series problem, you think forecasting. But there's also the problem of time series classification, in which the task is to apply labels to the time series. This is often done in a streaming setting, in which you need computationally efficient techniques. Something expensive is difficult or infeasible to use in your production system. Today on the show I speak with Angus Dempster about the algorithm MiniRocket. MiniRocket is something like a 75x improvement over Rocket. It uses convolutional neural networks to transform the data such that linear classifiers can be used to make the actual labeling task. We do a high-level dissection of MiniRocket and discuss some of the empirical results of this algorithm in practice.
My name is Angus, and I'm a PhD student at Monash University in Australia, working on scalable methods for time series classification.
Well, let's dive right in. Tell me a little bit more about the scalability aspect. What's unscalable about some of the more popular or maybe well-known procedures for doing time series?
There are many methods which exist to do time series classification, but one of the sort of issues that has existed in the field for quite a while is this issue of scalability. In particular, many of the most accurate methods for time series classification have been burdened by high computational complexity and a lack of scalability.
I know a lot of people have broad interests in looking at mini-univariate time series, so scalability can be challenging in two ways. Maybe I have thousands of signals I want to look at, and so although I guess they could run in parallel, there's still a scalability issue. And then there's the individual time series, where maybe it's, of only, 1,000 points, sounds pretty small in the big data world, but just as you were mentioning, the computational cost to it can be difficult. What are the real frontiers? Where are you pushing on scalability the most?
It's both. So we are looking at scalability in terms of the number of examples that you're trying to process, and also in terms of the length of the time series you might have. Exactly how you deal with this issue depends a little bit on context. So you'll see maybe the domain where you have the sort of the longest time series, or typically is in audio classification, which is kind of a specialized subset of time series classification. And audio, has a very high sampling frequency. So I think often in audio, for example, you have sort of specialized techniques which you use to deal with that. For example, often in audio, a typical thing that you do is to do a kind of pre-processing where you might turn your audio signal into a spectrogram and pass that to some kind of classification model. And that's sort of doing a kind of implicit downsampling of the input to deal with that.
And what is the nature of the expense? Why are some of these expensive? Where are you spending the time, generally speaking?
It really depends very much on the method. So there's quite a variety of methods which are at the forefront of time series classification. And it really depends on the particular method and where that time is spent. I guess our focus has been trying to mainly deal with it on the training side. And so then, different methods, they may be spending a lot of time trying to tune hyperparameters, or there may be something kind of inherent in the method which has a high computational complexity. And then the sort of single most accurate method is an ensemble of other models. And of course, that sort of brings in the complexities of all its constituent models. So that's another reason why there's high complexity in some cases.
Well, prior to the publishing of MiniRocket, what can you tell me about the state of the art in time series approaches? What were some of the main contenders a person might think to use when going at a big problem?
There's been a little bit of movement in the field, I'd say, over the last year or so. In around 2017, there was a big review paper that went through, for all intents and purposes, all of the methods which existed up to that point. And it identified a number of models which really stood out. So one, we would call it a dictionary method or a bag of words method, which is based on looking at the frequency of discriminative patterns in time series. Another one is called a shapelet method, or the shapelet transform, where you're looking for kind of discriminative subseries in time series. And another was a large ensemble method, which incorporated both the dictionary method, the shapelet method, and a number of other methods. Since then, there's been quite a bit of progress. There are methods which are based on distance measures, so that's where you perform classification by measuring the distance between time series with various distance measures, and those methods have been pushed quite a long way. There are also a recent method, what you would call an interval-based method. So that is where you're looking at sort of subregions of time series and extracting features from those subregions.
Well, can we focus on Rocket, since that's sort of pivotal to the contribution in this paper? What is Rocket?
Right, so Rocket is a method where we try to take a slightly bit of a different approach. And what we do is we take our input time series and transform them using a large number of random convolutional kernels, and then use the transformed features to train a simple linear classifier. So that's kind of the crux of Rocket and how it works. It turns out that this process, although it seems very simple, produces high classification accuracy and is quite fast and scalable.
Yeah, the appeal to me of that design is, okay, maybe I spend a lot of time training that convolutional neural network, but once I've got it, I've got it, and it's as big as I let it be, right? And once I have a linear feature, that's as efficient as you can get in your production system. So there's some obvious advantages for someone who wants to put Rocket in production. Is there a price for that efficiency and that good implementation? Do I lose accuracy or something like that?
The method has, I'd say, reasonably high accuracy compared to other state-of-the-art methods. I don't think you lose out on accuracy per se. I guess there's 2 points to make. The first is that no model is going to be, the be-all and end-all. So, no model is going to be the most accurate on every data set. And the second thing is, as it is a method which incorporates a lot of stochasticity, it is going to have some variability in the accuracy. So on each run, it's going to give a slightly different result. So I think that's probably the main thing to bear in mind from that point of view.
Can you contrast then what is MiniRocket in comparison to Rocket?
With MiniRocket, what we're really trying to explore is, I guess, 2 things. Firstly, what is really the importance of this randomness, this stochasticity in Rocket? To what extent can we take that away? So that's the first thing. And then secondly, how can we build on that in order to really, I guess, fulfill the promise of Rocket in terms of scalability? How fast can we make it? So with MiniRocket, we're going from a random to a largely non-random method. And ultimately, we're going to end up with a much, much faster method for time series classification.
That's interesting because broadly speaking, and maybe this is a weird bias I bring to the table, but I feel like in a lot of computer science work, injecting randomness has these advantages. It comes up in like probabilistically checkable proofs and stuff like that. De-randomizing doesn't always seem to have the same benefits. What's the key insight here where that gives you an advantage?
The takeaway in one sense with MiniRocket is that the randomness that we have in the Rocket method, while it is highly effective, is not strictly necessary. But the other sort of bigger picture takeaway is that, or this method in the way it works, so the randomness with Rocket is really all in the kernels. Basically, every aspect of the kernel is random. And with MiniRocket, that's not the case. But I think the sort of bigger picture item here is that the set of kernels that you use for a method like this is, the question of the set of kernels that you use is something of a red herring. And in fact, there's a lot of flexibility there. So you can use random kernels. You can use this small fixed set of kernels that we have in MiniRocket. And in fact, there's a number of different sets of kernels which work similarly and similarly well. So I think that's kind of the bigger picture takeaway, that a particular set of kernels you're using is not really of primary importance. There's lots of different sets of kernels which are going to perform similarly well.
And of those then selected for MiniRocket, how are those constrained? What are the kernels you're using there?
So we use a small fixed set of kernels, and we can see from experimentation that actually a number of sort of different sets of kernels are going to perform the job well, are going to produce high accuracy. So what we ended up choosing was just a relatively small set of kernels. They've all got the length of 9, so they have 9 weights, and they're restricted to having 2 different values for the weights, but they're not binary in the sense of having the values 0 and 1 or -1 and +1. In fact, our kernels are constrained to having the values -1 and 2, but actually, in fact, the particular values, the magnitude of the weights in this model doesn't really matter, subject to a couple of constraints. But yeah, that's the kernels we're using.
Makes sense. You'd mentioned arriving at those in part through experimentation. What were the underlying data sets you experimented on?
The field of time series classification is really being built on work to produce a big repository of data sets that everybody can use to develop their methods and ultimately to do benchmarking and demonstrate the efficacy of their methods. So that's work that has come out of mainly 2 groups. So that's work by Professor Eamon Keogh at the University of California, Riverside, and also work by Professor Tony Bagnall and his group at the University of East Anglia. So they've built up this archive called, commonly known as the UCR archive, which is kind of the benchmark collection of datasets for time series classification. And it contains a whole mixture of different types of time series datasets. So you have datasets which are sort of motion sensor datasets to do with activity recognition. You have datasets which are sort of spectra. You have datasets which are to do with sort of medical data, a big variety of datasets. And this sort of comes back to a sort of interesting observation if you take a step back and sort of look at this field in context. So I think an interesting observation here is that something like a field like image classification, for whatever reason, is typically benchmarked on a relatively small number of relatively large datasets, whereas time series classification, for a variety of reasons, has really developed in a way that benchmarking tends to be done on a relatively large number of relatively small datasets. That is changing slowly. I think it's still good to have a mix of large and small datasets because it provides a kind of a different challenge. But yeah, historically, this archive has contained a large number of relatively small datasets, but now larger datasets are starting to be added to it.
Thanks to this week's sponsor, Quantum Metric. To all the digital leaders out there, how would it feel not only to know what your customer is experiencing, but how many others are experiencing this too? I think it's about time we put our customers at the center of our decisions and get ahead with real-time insights, way before a code freeze. It might be beach weather outside, but for retailers, the holiday season has already begun. 2021 holiday e-commerce sales are expected to exceed 2020 benchmarks. Are you prepared to capture every customer revenue opportunity? With Quantum Metric, you can be. Their unique approach to the digital customer experience helps today's top retailers and e-commerce brands quickly identify and prioritize the big and small revenue opportunities that keep customers engaged and coming back. Stay off the naughty list this upcoming holiday season by reducing customer friction, increasing conversions, and personalizing the shopping experience. Want a sneak peek? Visit us at quantummetric.com/pod offer and see if you qualify to receive the 12 Days of Insights offer using the code SKEPTIC, all caps. This offer gives you 12-day access to their platform coupled with a bespoke insights report that will help you identify where customers are struggling or engaging in your digital product. Some restrictions apply. If you're doing anything related to e-commerce, you've got to have a look at Quantum Metric and see if it suits your needs. Head over to quantummetric.com/pod offer, and while you're there, use the code SKEPTIC, all caps. Thanks to this week's sponsor, Seamless ML. Are you a data scientist, Kegler, physicist, mathematician who wants to be a data scientist, or quantitative researcher? Seamless ML is looking for exceptional people to join their team. The team is already stacked with one of the best poker players in Europe, one of the best cosmologists of his generation, and a top 20 Sudoku player in the world. Seamless ML is applying machine learning to do algorithmic trading. That's a challenging but incredibly rewarding project. If you're deeply committed to excellence in machine learning, this team could be the place for you to leverage your training and take the next step in your career. To learn more, head over to seamlessml.com/jobs. That's seamless, SEAMLESS, ml.com/jobs. When I'm looking at Table 1 of the paper that compares Rocket and MiniRocket and some of its features, one thing I can say is pretty much every row, Rocket is in a more constrained position, right? You go from 20,000 features in Rocket to only 10,000 in MiniRocket. And Rocket has randomness where MiniRocket must be fixed. So everything is kind of constraining. One might expect it's going to perform worse under all these constraints. What are the actual results?
The results show that MiniRocket, more or less, basically on par with Rocket in terms of accuracy. And in fact, the results for each of the datasets, it's quite similar. So it's basically performing very similarly overall. And I think what that shows is that it's really coming down to the sort of overall procedure and what is happening there. So the fact that the results are similar show that you can sort of make these changes. Changes are made really with a focus on scalability, but that in a sense, the core of the sort of information that you're getting out of this transform is very similar. And so that you can still maintain this high accuracy and get very, very similar results.
So if I have similar accuracy, that's very appealing to me. What do I gain in terms of improved training time?
So this is going to depend a little bit on, how big your data set is in terms of how many time series you have, and then the length of the time series. So overall, basically, the larger the data set is, the bigger the advantage that MiniRocket is going to have. Essentially, what MiniRocket represents is a large constant factor reduction in training and inference time over Rocket, but that reduction is very large. So it's approaching 2 orders of magnitude on larger data sets. So I think for a very large data set, it's sort of up to approximately 75 times faster than Rocket.
Well, if I can train faster and I get more or less the same accuracy, is it correct to call this a free lunch?
Yeah, possibly. You're getting essentially the same results. So I think it really makes sense to treat MiniRocket as kind of the best version of Rocket. So I'd say what MiniRocket, in a sense, really does is to fulfill the promise of Rocket in terms of speed and scalability. So doing the work with MiniRocket, we realized there are a number of ways which the procedure can be really aggressively optimized. So yeah, you're getting a massive benefit in terms of speed and getting essentially the same results in terms of accuracy.
Could we dig into some of those key insights? Where do the speedups really come from?
The speedups in terms of MiniRocket over Rocket are due to really 4 key optimizations. So the first is not strictly speaking an explicit optimization so much as a way of avoiding doing a whole lot of work in the first place. So this comes down to, and this is based on a property of the pooling mechanism we use. And pooling mechanism produces what we call PPV features for proportion of positive values. And this optimization is based on an observation that these features have a kind of symmetry, in that if you know the proportion of positive values, then that's 1 minus the proportion of negative values. And what that means is that if you produce a PPV feature for some kernel, let's call it W, then that's really closely equivalent to a feature that you would get if you were going to do the same thing but for the negative that kernel, negative W. What that means overall is that we can basically get away with using half the kernels that we would otherwise have to use, because every time we produce a feature for one kernel W, it's sort of equivalent to a feature that we get for the negative that kernel. So we don't actually have to do the procedure for the negative kernel, negative W. So we're kind of using half the kernels overall that we'd otherwise have to use. That's the first optimization. The second optimization, again, comes back to how we are performing pooling. So what happens in earlier method Rocket and what is typical in convolutional neural networks is that, you have some convolution output, some feature map. You perform pooling, and then if that's a global pooling, you get a single feature. When we perform pooling, we are reusing or recycling the convolution output multiple times. So we get our convolution output, and then we're going to use that to produce multiple features. So we get multiple features for the cost of one convolution operation, basically. The third optimization is performing convolution by addition. So this is a fairly standard kind of optimization you see in some binarized and quantized convolutional neural networks. And basically, the convolution operation involves doing, you can think of it as a sliding dot product in terms of time series between your kernel, which is like a vector of values, and your time series. So if you imagine your kernel at any particular position on your time series, it's doing a dot product. And then you do that at each position in the time series. But that involves repeated multiplication and addition. However, if your kernel is limited to a relatively small number of weights, here we're limited to just having 2 different values for our weights, but it doesn't have to be just 2. You can kind of factor out the multiplication aspect. You can do all of your multiplications kind of upfront, and then when you want to perform convolution, all you're left to do is addition. And if you think about the convolution operation or doing a transform like this in terms of a kind of set of nested for loops, what that basically does is it's taking the multiplication from one of the inner loops right to the kind of outer loop. That's the third optimization. And the fourth optimization is basically like a little trick. It's building on this idea of convolution by addition. So in our method, we take our input time series and we convolve it with our small fixed set of kernels. But each kernel is going to be applied with multiple different dilation values. So what we do here is we treat dilation as the outer loop. And what we do is we kind of pre-compute a convolution output where we pretend, for a given dilation, we pretend that all the values in the kernel are -1. So that's one of our 2 different values for our weights, -1 and 2. So we pretend all of the values in our kernel are -1. We pre-compute this for each dilation. Then when we go to compute the final convolution output for a given kernel, all we have to now do is compute a little correction, which is based on where the values of 2 are in our kernel. We compute this kind of intermediate representation once for each dilation, and then for each kernel, we only have to compute this little correction. And the key point here is that this correction that would otherwise be required to compute the convolution output for the full kernel. So what that means overall, in essence, is that you're getting the convolution output for approximately 2/3 of your kernels essentially for free. So they're the sort of 4 key optimizations which MiniRocket uses, and they're really built on the simplicity of this small set of kernels. And that's what really makes it so much faster than Rocket.
Yeah, all 4 of those key optimizations seem, in some sense, generalized. I don't think they're necessarily specialized to Rocket. We see convolutional neural networks showing up in other techniques and things like that. Do you imagine that some of these techniques will be lifted and applied under other methodologies as well?
Well, in some sense, some of them at least are really just highly simplified forms of optimizations which are already used in some other methods. So yeah, I think there's definitely broad applicability. But with MiniRocket, I guess the key thing is that they're really natural optimizations which are very easy to apply when you have this small, very simplified set of kernels. So I think things are going to get more complicated if you're trying to turn them into kind of more generalized optimizations.
What do you see as next steps? Will there be a MiniRocket v1.5, or is it all about applying it to different domains?
No, I think we're definitely interested in taking the methods further. Exactly what that's going to look like, I'm not sure. I mean, again, one sort of overall point with methods like this is that nothing is going to be, the best method for every possible data set. So there's always kind of things that you can work on to expand the sort of applicability of these methods. We have a number of things which, we know that kind of shortcomings of the method in some sense. There's a lot of room still to improve. I think we'd like to take these methods further. Exactly what that's going to look like, I'm not sure yet. And then we're also interested in, really exploring other methods as well to see, what we can bring to the field.
Well, maybe to wrap up, could you talk about the long-term goals? Like, what do you see as the horizons or the real cutting edge in time series exploration?
One of the interesting things about time series, and this is not an original observation to me by any means, is that in an important sense, time series classification as a task in some ways very similar to image classification, albeit in sort of one less dimension. And so the observation has been made that methods which work well for image classification, we should have really quite a strong expectation that perhaps with some modification they should work also for time series classification. And I think bearing that in mind, I think perhaps what we might see, I'm not sure, exactly when, but as some of these new cutting edge methods that are coming actually originally from sort of NLP, then to image classification, I think ultimately we're going to see that come into time series classification as well. So what I have in mind here are transformer models, mixer models, things like that. I think there's a lot of potential for that to be explored in the field of time series classification. So my expectation is that's going to be one of the main changes that we see over the next few years. There are some interesting challenges with that because as similar as they are, there are some important differences between, for example, image classification and time series classification. And I think there's some really sort of key issues to try and crack to apply these methods that are coming from other fields into time series classification. I think the two things in particular that I have in mind are really working out what is an appropriate kind of embedding for time series to be used with transformer-like models. And secondly, if we were to look at a model like the MLP mixer model or the similar models that have come out recently, how you're going to deal with the information being mixed across the time dimension. So when you apply like a mixer model or a transform model to images, what's typically done is that the image is cut up into patches. And I think that particular procedure is probably going to be a bit of a problem when you try to apply it to time series. So I think there's big challenges there, but I think, that's my expectation of where maybe the field might go, at least in one direction.
Yeah, some very exciting research paths there for sure. Well, Angus, where can people follow you online?
The best place would be to go to our GitHub repository for the MiniRocket method, and you can also contact me by email.
Awesome. And tell me a little bit about the implementation there. What language and what's it take to get started?
MiniRocket is coded in Python. What we do, though, is we apply just-in-time compilation. So we're using the number library for that. But in terms of sort of reading the implementation, it's essentially pure Python and NumPy. But I think if people want to get started in time series classification more generally, I think I would suggest checking out a couple of the prominent libraries in the area. So one is the skTime library. That's an offshoot of the scikit-learn library. and that it's got a lot of capability way beyond time series classification, but there's a lot of the kind of core time series classification methods are implemented there. And it's also a very active library, so it's a great place to start. And I'd also suggest people check out the TSAI library. So that's like an unofficial time series library for fast.ai. You can find them both on GitHub. I think, yeah, they're both excellent projects.
Well, good suggestions. Angus, thank you so much for taking the time to come on the show and share your expertise.
Oh, my pleasure. Thanks for having me.
That concludes another installment of Data Skeptic Time Series. Thanks to our sponsors today, Quantum Metric and Seamless ML. Our guest today, Angus Dempster. Myself, Claudia Armbruster as Associate Producer. Vanessa Bly, Guest Coordinator. And our host, Kyle Polich.